Hello students, we continue your lectures on mathematical physics. I will discuss about Fourier series here. Now, what the Fourier series says is that if we have any single value periodic function, uh, so it can be represented as a summation of harmonic terms. Can represent this as a summation of harmonic terms which are multiples of that of the given function. So if we have a function fx, uh, the function fx, and it is say represented in the interval minus pi to pi, then you can write fx as equal to 1 by 2 into a0 plus summation n is equal to 1 to infinity an a0 cos nx an cos nx plus bn sin nx. So these are the harmonic functions. So any periodic function can be represented as a summation of harmonic functions where the constants or the Fourier coefficients an and bn are represented as so we can write an as equal to 1 by pi minus pi to plus pi fx cos nx dx and similarly you can represent bn as equal to 1 by pi minus pi plus pi fx sin nx dx, where n is a quantity which runs from 0, 1, 2, 3, like that. Now this is where the fx is being defined in between minus pi and pi. It can be also the case that instead of minus pi and pi, you have minus L and L, then the Fourier transform or the Fourier series will be written in a different manner, and it will be the same thing, but the representation will be a little different. So in that case, so where the fx will be presented as 1 by 2a0 plus summation n is equal to 1 to infinity an cos n pi x by L plus Bn sine n by x by L. And so this Fourier is defined in the interval between minus L to L, and it has got a period of 2L. So here again the Fourier series, the Fourier coefficients will be a little difference. Instead of pi, we have minus pi to I, have interval is minus L to L. So n will be equal to 1 by L integration minus L to L fx cos n by x by L dx, and Bn will be equal to 1 by L minus L to L fx sine n by x by L dx. So this is how they present Fourier series. You can also represent the Fourier series in complex form. So in the complex form, the Fourier series can be presented as fx is equal to n is equal to minus infinity to infinity Cn e to the power I n by x by L, where Cn is having the value 1 by L integration contour plus the interval 2L into fx e to the power minus I by x by nx by L dx. Now this value is Cn, which is, let me write it once again, it is 1 by L C to C plus 2L fx e to the power I by n x by L dx. This has got two values. One is if it is and n is more than 0, then if we can write it as 1 by 2 an minus I bn if n is greater than 0, and 1 by n a minus n plus I b minus n if n is less than 0, and 1 by 2 a0 if n is equal to 0. So there are three conditions. So this is the Fourier series. The next is your Fourier transform. So we are now moving on to integral transforms. There are basically two types of transforms. One is Fourier transform, and another one is the integral transform. These are the most common transform. Fourier transform is physically it's actually changing the coordinate system. That means you basically do Fourier transform between the real space to momentum space, or the time space to frequency space. This is the physical significance of the Fourier transform. So mathematically you can write the Fourier transform in the following way. Suppose you would like to do a Fourier transform of a function fx. So Fourier transform can be written as f of fx can be represented as, let's say it's now f of alpha, and it is equal to minus infinity to infinity fx e to the power I alpha x dx, and this quantity e to the power I is called the kernel of a integral transform. So like we have a Fourier transform, we have an inverse Fourier transform is when f alpha is being transferred to fx. So for that, we are now doing the Fourier transform of, say, f alpha. It is equal to, say, f of x, and it is now equal to 1 by 2 pi minus infinity to infinity f of alpha e to the power I alpha x dx. So there are two things which needs to be seen. First of all, in the inverse Fourier transform, let's call it as 1 by. In the inverse Fourier transform, the differences that we're observing is, first of all, addition of this 1 by 2 pi and the change of sign. Okay. Now, if say the Fourier transform in many cases can be written is like f of fx, sometimes this is represented by these two coefficients minus I alpha x. If this is the case, then the inverse Fourier transform will not have this, and the sign will get changed. So there are two aspects. One is having this factor being multiplied at the front and the sign of the kernel, whether it will be plus or it will be minus. These two things will be kept in mind. So if it is the first case, in the opposite, it will be second. Now the idea is the multiplication of Fourier and an inverse Fourier transform in terms of 2 pi will fetch you 1 by, will give you 1 2 pi, and in terms of kernel should give you the value to the power 0. This is the idea behind it. So fx and f alpha, fx and f of alpha, they are called Fourier transform pair. So we can have different values of x and corresponding to having different values of alpha. Suppose if we have 1 by x square plus a square as the fx, then the value of alpha will be pi e to the power minus alpha a divided by a. If it is, say, x divided by x square plus a square, then it will be minus a e to the power pi I alpha e to the power minus alpha a, and if it is 1 by x, it will be pi by 2. If it is e to the power minus ax, it will be a by e to the power alpha square plus a square. It is similar to what has happened here. And if it is minus e to the power minus ax square, it will be 1 by 2 into root pi by a e to the power minus a square by 4 alpha minus alpha square by 4a and if it is x into e to the power minus ax square, then the Fourier transform will be root pi divided by 4 e to the power 3 by 2 alpha into e to the power minus alpha square by 4a. So these are some of the Fourier transform pairs.